Hello viewers, welcome to my channel VK Civil Hub. I am Professor Vinod Kumar from the Department of Civil Engineering. In the last video, we saw analysis of bars of varying cross sections. In today's video, we are going to see how to analyze bars of varying loads at the sections. Let's get into the problem. A steel member of uniform cross section 25 mm in diameter is suspended vertically as shown in the figure. It carries a load of 10 kN at its lower end and loads of 20 kN and 15 kN at the points indicated in the figure. Determine the total elongation of the bar if E is equal to 2 into 10 power 5 Newton per mm square. Here you can see the diagram which clearly represents the question. It consists of three sections 1, 2 and 3. One is of 0.75 meters length. Section 2 is of 0.5 meter length with a load 15 kN at the junction, and section 3 is of 0.75 meters with a load 20 kN at the junction, and another load 10 kN is acting at the end of the bar, and the whole bar is fixed on the top. Let us start with the given data. L1 is given as 0.75 meters, that is equal to 750 mm. L2 is 0.5 meters, that is 500 mm. L3 is equal to 0.75 meters, that is 750 mm. Here the dia is constant throughout, so D1 is equal to D2 is equal to D3, which gives D as 25 mm. And the Young's modulus is also common, that is E1 is equal to E2 is equal to E3, E is equal to 2 into 10 power 5 Newton per mm square. With the help of the diameter, A1, A2 and A3 are same, which gives you A is equal to pi by 4 D square, that is equal to pi by 4 into 25 square, which gives you 490.87 mm square. Here we have to find the change in length delta L. So this is the bar given in the problem. We are going to split all the three sections into separate parts. That is, we are drawing free body diagram for each and every section. Let's consider the third section wherein you have a 10 kN load. So in order to maintain the equilibrium condition, this 10 kN force has an opposite 10 kN force on the top. So the section 3 is a free body diagram with 10 kN on both the sides. Coming to the section 2, in the problem it is given as 20 kN at that junction. But for the free body diagram, we have 10 kN as equilibrium load. So we are marking it as x kN. That is what we have to find. How to find this particular load? Here, which is marked in the circle, x kN and 10 kN. We have to take the difference of this and equate it with this 20 kN load at the junction. So what happens? X kN minus 10 kN gives you 20 kN, which gives you x is equal to 20 kN plus 10 kN. That is 30 kN is your x force. So here the force is 30 kN, and to maintain the equilibrium condition, top also we are putting 30 kN. So this second section is over. Coming to the third section, we don't know that value also. We are comparing 1 with 2. So that y kilonewton is an unknown kilonewton, we have to find it, which is marked in the circle. The same process, the difference between these two should be the load at the junction, that is y minus 30 is equal to 15 kilonewton, which gives you y is equal to 15 kilonewton plus 30 kilonewton, that is 45 kilonewton. So for the section 1, the load we are getting as 45 kilonewton. And in order to maintain the equilibrium, on top we are putting 45 kilonewton. So now we have arrived at the free body diagrams for the whole structure. With these three free body diagrams, we are going to calculate the change in length for each section and adding up together to find the final change in length of the given problem. So here the total change in length delta L is equal to delta L1 plus delta L2 plus delta L3. In the problem, area is common, E is common, So from the formula delta L is equal to PL by AE, we are taking that AE outside. So 1 by AE will be common for this problem. We are having different values of loads and different values of lengths. So inside this formula, that is PL will be remaining. P1 L1 plus P2 L2 plus P3 L3. We have to substitute all the values for this. We have A is equal to 490.87 and E is equal to 2 into 10 power 5. So 1 by 490.87 into 2 into 10 power 5 whole into P1 is 45 kilonewton. Here we are getting it converted. So 45,000 into 750 plus 30,000 into 500 plus 10,000 into 750, which gives you 0.573 mm. That is the result of this problem. That is the total change in length delta L is equal to 0.573 mm. Let us see one more problem which goes like this. A member is subjected to point loads P1, P2, P3 and P4 as shown in the figure. Calculate the force P2 if P1 is equal to 45 kilonewton, P3 is equal to 450 kilonewton and P4 is equal to 130 kilonewton. Determine the total elongation of the member if modulus of elasticity is 2.1 into 10 power 5 Newton per mm square. So this is the given question and the diagram given is as shown here. There are 4 loads P1, P2, P3 and P4 with different areas and lengths. Here you have to make a note. P1 and P3 are acting towards left, P2 and P4 are acting towards right. So this is where the condition we have to use it to find the force P2. Let's check what are the given data. P1 is equal to 45 kilonewton, P2 is unknown, we have to find it. P3 is equal to 450 kilonewton, P4 is equal to 130 kilonewton. Here these loads are not converted because this will be easy to put as it is in the problem in the diagram to explain So while expanding this we will convert it into Newton. Length of section 1 is given as 1200 mm converted. Length of section 2 is 600 mm. Length of section 3 is 900 mm. Your E value is 2.1 into 10 power 5 Newton per mm square. And the area of section 1 is 625 mm square. Area of section 2 is 2500 mm square. Area of section 3 is 1250 mm square. So with this given data, first let us find out P2 and then we'll work out the problem for the 3 sections equilibrium conditions as we did for the previous problem. So here's the diagram once again. As I said earlier, there are 2 forces acting towards left and 2 forces acting towards right. So here, in order to maintain the equilibrium, the left side forces are equated to the right side forces, wherein we can find the value of P2. That is, P1 plus P3 is equal to P2 plus P4. P1 and P3 are acting towards left, P2 and P4 are acting towards right. So we are equating these two. From this, 45 plus 450 is equal to P2 plus 130. 495 is equal to P2 plus 130. We are getting P2 as 365 kilonewton. So one part of the problem is over. Now, how to split up this whole section into free body diagrams? Let us see what happens. First section is taken. The load P1 is 45 kilonewton, which is given in the problem. So the equilibrium load on the opposite will be 45 kilonewton. So this particular section free body diagram is this, and we don't have to convert anything. And the last section of the problem, which is shown in the blue color, the last load, that is P4, is 130 kilonewton. So for this particular body, 130 kilonewton opposite is taken here to maintain the equilibrium. Now the problem is the center section, that is this yellow color part. We have taken x kilonewton on both sides and we are going to find this x kilonewton so that we can find the change in length in each section. So how to find this x? As I explained already in the previous problem, this particular section, that is the difference between 130 kilonewton and the x kilonewton, should be equal to this value of P3. P3 is the load at this particular junction. So what happens? 130 minus X gives you 450 kilonewton because P3 is 450. So solving for this, we get X is equal to minus 320 kilonewton. Why we are getting X as minus 320 kilonewton? The negative sign indicates a contraction or a compression. Okay, so that particular delta L we have to take it as minus in the equation. I will tell you a little later. Now the total change in length delta L is equal to, the normal formula is delta L1 plus delta L2 plus delta L3. Okay, here we are getting the second section as a minus sign, so that indicates contraction, and here we have to take minus delta L by 2. So what happens now? 1 by E is taken as common outside because E value is same for all the sections, and inside PL by A. Here also the formula is delta L is equal to PL by AE. Don't forget that. So inside PL by A value is changing for each section. So 1 by E into P1 L1 divided by A1 minus P2 L2 divided by A2 plus P3 L3 divided by A3. So next what happens? We know the value of E is equal to 2.1 into 10 power 5. Substitute it here. The value of P1 is 45 kilonewton. Here we are converting that value into Newton. So 45,000 into the length is 1200 mm divided by area is 625 mm square. This is for the first part. For the second part, here the value for the second section is 320 kilonewton. So 320 into 10 power 3. 3,20,000 into length is 600 and the area is 2500 mm square. For the third one, it is 130 kilonewton. So 130 into 10 power 3 into 900 divided by 1250. So we are getting as 1 divided by 2.1 into 10 power 5 into 86,400 minus 76,800 plus 93,600. You are getting it as 0.4914. And the result for this is the total change in length delta L is equal to 0.4914. Okay viewers, I hope you liked the video. If you need the video for the varying bars of different cross sections, I have given the link in the description. You can go there and watch it, and please leave your comments for my next videos. Thank you.